Welcome back. Because classical set theory lies between the spectrums of the most computational and the most realistic to data, it's often useful to ground a lot of our concepts in this classical model. It's also the place that has the most mature mathematics to go with it. To remind you, classical sets means that the judgment of being an element is true or false. Perhaps the most important operation isn't even one that sounds like an operation. It's to test equality. What does one set of data equal another set of data? Since we only have one rule in set theory, the judgment of element of, we have to base everything off of that. So we can do that with the following notation. If the only judgment we have is being a member, then to say that S equals T means that every judgment we could make of S is a judgment we could also make of T. So, said another way, if X is an element of S, then X must also be an element of T, and vice versa. If X is an element of T, then X must also be an element of S. Now, you'll often find that this is accompanied by some notation. For example, when X is an element of S, then X is an element of T can be said as S is a subset of T. The statement that X is in T means X is in S is a statement that T is a subset of S. Therefore, it is common to summarize that S equals T when S is a subset of T and T is a subset of S. Jargon alert, this is what's known in set theory as the axiom of extension. You won't need to use that name, but just know that this is how we are often expected to show that two pieces of data are the same. You'll discover that your data actually form two classical sets. You then show that one is a subset of the other and vice versa. If you do this, you get to conclude that S equals T. Keep in mind the essential thing here is that we have a classical set where judgment is truly just about true and false. No in-between values, no missing values either. So what are some of the consequences of equality between two sets? Some of the consequences may be surprising, because it may be that you were taught sets by different people over different times. They may have presented in a different way. Instead of focusing on the judgment element of, they may have focused simply on some notation that they call set notation. For example, it's not uncommon to find textbooks that describe a set by listing things inside of braces, as if braces have anything to do with it. This is just a notation for the various sets. What it's really trying to do is give you a coded way of describing elements of. When we write things with these braces, we're saying that everything that occurs separated by a comma counts as one of the elements. That is, I could take the number 7 and judge that it's in this set, because I find it in this list. But if I was to take the number 5, I don't find it in this list, I would judge it's not in there. Now, instead of check marks and X marks, the typical notation for not in is to strike through the element of symbol. So here we are at a classic situation. You may have even seen this before in your own education. You may have been asked, are these two sets equal? And as classical sets, they are. The way we should judge that, however, has a lot to do with how you're taught. Let's go through the test using what we have as our rule for equality. Our rule for equality says that two sets are equal when their judgments are the same. What are the judgments possible? Over here, I can judge that 1 is an element, 2 is an element, and 3 is an element. Every time I check that there's a judgment here, there has to be a matching judgment over here, and vice versa. When 1 is an element, I see that 1 is also an element. 2 is an element, and 2 is also an element. 3 is an element, and 3 is also an element. So these are equal sets. Now the nuance emerges because many mathematicians can't help but think computationally when they read this. For example, they might notice and witness the difference between checking how 1 is in here. 1 occurs as the first element, whereas over here, 1 doesn't occur until much later. This prompts many mathematicians to make a phrase something like, sets don't care about the order of elements. Another thing they might observe is that the number 2 appears in different quantities. So again, computationally, in terms of resources, 2 is overabundant than is needed to describe this set. That causes mathematicians to also say sets don't care about multiplicity. The truth is that we're fuzzying the logic here. Content like the number of resources require logic that cares about resources, logic without weakening rules. We saw this in our linear logic, quantitative logics in general. Also, the placement of the numbers not being important is a judgment about intuitionistic logic. We care about how a program actually runs. This is classical, we just care about the judgments being true or false. So, while it is true that sets don't seem to care about the placement of the numbers or the multiplicity, That's an artifact of having read this entirely wrong. You're reading into this picture some intuitionistic, quantitative, or other types of logical questions. You're seeing a program you would have to run, and then you're asking for when two programs produce the same classical output. That's not the question being asked. The question being asked is simply, are these two classically the same? Do they judge the same way? The result is that two programs could give you the same set with completely different mechanics. That should be no surprise at all. The warning I want to give you is that it's not an effective strategy to try to describe classical sets by using other types of logic. If you focus and fixate on the programs that produce the sets, you'll find that there are many programs that you don't know how to compare. You can't decide whether two sets are equal if you're trying to compare two different programs. Comparing programs is quite hard. Focus on the judgments. The programs are not a relevant piece of this. So while it's not incorrect to observe that sets don't care about multiplicity and don't care about the order of the elements, it's not even part of a possible question of sets. Those statements don't even belong to the classical canon of logic. They belong to a different kind of logic, and therefore, mentioning them at all has nothing to do with equality of sets. Let's move on to another operator between sets. Each operation in set theory is related to some classical logical operator. So let's look at AND. It turns out it produces two related kinds of sets. The first one we've explored as ordered pairs. We can see that every term in here as an ordered pair belongs to something from A and something from B. So the AND is capturing the fact that both things are there together. Notice this set takes our A and B and makes a much bigger set by combining both properties together. It's one version of the word AND. But there's another version, and it's important not to confuse them. The second type of AND is to take the intersection. Here we look at A and B as two separate sets, but we look at the judgments to agree on some part of it, a subset of the data. We take all the points C, which happen to lie in A as well as in C. This is a different use of AND than we see up here. In particular, we make the sets that are smaller. So our first AND here is to take the data and multiply it this way and that way to create ordered pairs that pinpoint everything based on two parameters, A and B. The second version is to look for properties that have A and B in common, the intersection. Don't confuse these two. The products get larger, the intersections get smaller. What about OR? When we switch to the OR operator, we also get two types of sets. The first one might be called the disjoint union of A and B, or also denoted as A plus B, depending on the type of topic. In here, we simply label the data as coming from the A or the B. So we have in A or in B. These are also commonly called in left or in right, based on the size of these. Or mathematicians prefer the words iota A and iota B. At the end of the day, this is a larger set than A or B. It takes both of these and puts them together. The union, on the other hand, is to take A and B, but not double count the intersections. There might be values that are already in both of them. They only show up once. So this one's called the union. It can be confusing to remember all these, so let's use some diagrams. So here we have it. Our Cartesian product is best modeled like a Cartesian plane, meaning it's got an x and a y axis, only now the x is played by A and the y is played by B. We put in dots to indicate every single coordinate. Sometimes it's actually discrete points like this separated with spaces. Other times this is a schematic diagram. It might be that there are so many points in there that it's infinite. Don't overthink the picture. This is just to give you an imagination. You see that the size of the set is getting bigger, and in proportion to the size of A times the size of B, because every single point is indexed by both an A and a B. That's our first AND metaphor. The second AND metaphor gets smaller. We have a larger set A and a larger set B, and we want the points that are in both of them. The AND now is about where they are as members. Up here, this is about what they are as data types. Down here, what they are as classical sets, with the judgment of membership. Likewise, when we go to OR, we see a different metaphor. Here, when we do OR as data types, we're saying, are they on the left or are they on the right? How were they introduced to us? So we could have some points on the left, which are in A, and some points on the right, which are in B. It's a disjoint union. Both sets come together and make a slightly bigger set. Not as big as the Cartesian product typically, but still bigger than A and B individually. Compare that with the union. Union goes back to classical set theory, so it's all concerned with membership. Is something a member of A union B? In that case, it's the shaded region because it needs to be in A or in B. Keep in mind, in classical logic, OR can be true and true. So the overlap is allowed to be in there, but it only counts as one extra copy. There are many other logical operators that we've explored and that we will explore. Each one of them has an impact on a type and a set. Keep these in mind and draw your own pictures as you build, and you'll start to get a pretty good understanding. The takeaway message is, every logical operator corresponds to a construction of data types and sets. So there we have it. We can divide our constructions into which logical operator and which type of data we're exploring. Together, we get a full picture. Until next time. That's how you take care of your chalkboard.